Hey guys, what's up? My name is Gabe and this is Games with Gabe, and this is the next episode in the Coding a 2D Physics Engine in Java series. So in the last episode what we did was we finished up some math for rotations, and then we also finished up our point versus primitive test. In this episode we're going to do our line versus primitive test. There's only two of them, three, line versus box, line versus rotated box, and line versus circle. But these three are pretty difficult because of the mathematics behind it, and we're going to take a look at all of that and how they work. So yeah, let's get started by checking out how a line versus circle works to see if a line is intersecting with a circle. First up, we have line versus circle. How can we tell that this line is intersecting with this circle? Well, the first thing we could do is we could just check and see, is the end point or the start point inside the circle? Because we already have a function that determines whether a point is inside a circle. But as this scenario shows us exactly, this isn't going to necessarily tell us whether the line's intersecting the circle, because neither of these points is inside the circle, but the line is still intersecting the circle. So what's our next course of action? What do we do next? Well, we can find the closest point to the circle, which would be this point right here, the circle center specifically. And we can look at this point and say, is this point inside the circle? Well, yes, that point is inside the circle. And this, without fail, will tell us whether the line is intersecting the circle or not. Because if we get the closest point to the center of the circle, then that needs to be inside the circle. If it's outside just a little bit, then we know for a fact that it's not going to be intersecting. But how do we get this point? What do we do to find this point? Well, we can use one of the mathematical tricks called projection. So what we would do is we would draw a line from this point to the center of the circle. And now we have this line. How can we project this line onto this line? That's what it's called. We're projecting this line onto this line, which basically means we just take its endpoint and we sort of smush it down perpendicular to this line, which gives us this point exactly. Well, we know we can get this vector easily too, because all we would do is we would subtract 8 minus 0, 0, which would give us this vector. So we just subtract the circle center from the line start. So center minus line start gives us our vector v, which is the circle to the center. And then to project it, we need to find out how to get this onto this point. Well, we can use the dot product. So remember that a dot b equals the magnitude of a times the magnitude of b times cosine of theta. And you may be thinking, how the heck does this help us at all with something like this? Well, look at this. We have magnitude of a and magnitude of b. If we can somehow get the magnitude of a with respect to the length of b and figure out what percentage he takes up, we know exactly where this point is. Well, how do we do that? Think about this. Let's call this vector a, and we'll call this vector b. What if we do a dot b over b dot b? Well, let's expand this. So a dot b would end up looking like magnitude of a times the magnitude of b times the cosine of theta. B dot b would look like the magnitude of b times the magnitude of b times the cosine of theta. Then we can cross this out, because those divided by themselves is 1. And what we're left with is the magnitude of a over the magnitude of b. Now you may ask me, if all we wanted was magnitude of a over magnitude of b, why don't we just do that? Why don't we just compute this exactly? Well, remember, this takes a square root. And a square root can take upwards of 100 CPU cycles. That's a long time, and especially if we don't need to do that, considering we can do this, which is just literally 2 multiplications and 2 additions. So 2 times 2 plus. The computer can do this really fast, like 10 CPU cycles. So if we use this little trick, we can calculate the same exact thing just by doing a dot b over b dot b instead of doing the whole square root with this. And then what does this give us? Well, let's think about this. If we have 2 lines, we have a line here, we have a line here. If we take this length divided by this length, what this will give us is some percentage. So this looks like about 0.7 is what it would be. And this is like 70% of the line, right? And so that's exactly what this is going to give us. If we do a dot b over b dot b, it's going to give us some percentage, which would probably be like something like 0.5 of the line. It's about 50% in between. And then how do we get this point from there though, right? So that gave us the percentage, but it didn't quite give us the exact point. Well, now we can use that percentage, just multiply it by this direction, and figure out exactly where it is. And that's pretty easy. So we have this vector, right? This is just vector b. So what we can do is we can just say, okay, let's multiply v by 0.5. And remember, this is like a scaling operation. So what it's going to do is it's literally going to shrink the vector so that it looks like this. And then we can just say, let's add the line start plus this, and that will give us this exact point, right? Because if we just say, do this plus this length, what we're going to do is we're going to get to this point directly. Okay, so the exact formula that we're going to be using is a dot b over b dot b to get us t, which we're going to call our parameterized position. Then we can use t just by multiplying t by b, which will give us a scaled vector. And if we add that scaled vector to the starting point, then we end up with the closest point to the circle. Then we can literally just use our other function and say, is this point inside the circle? And if it is, we have an intersection. If it's not, we have no intersection. Okay, so let's code this. I'm back inside of our intersection detector 2D class. Now let's create a new function, and we're going to call this public static boolean, and we're just going to call it line and circle. And this is how we're going to sort of prefix all of our intersection, line and or box and something like that. So we'll say this takes in a line 2D, which is a line, and then this also takes in a circle. And we're literally going to do what we just talked about. So first we're going to say if the point in circle, and we're going to check the line start, and that is get start, or line point in circle, and we're going to check the line's end, so line.getEnd. So if either of these is inside the circle, then we want to return true, because we know immediately the line is intersecting. And we actually need to pass in the circle here too. So point in circle, and we need to do point and then circle. So pass that in as well. So if either of those is true, we can return true immediately, break out of this. If not, we have to go and do the extra steps that we talked about. So we'll say vector 2f ab, which this is going to be like the line segment. We're going to say is a new vector 2f line.end or line.getEnd dot sub line.getStart. And remember, we wrap this in a new vector. Always wrap it in a new vector, because if you don't, you will be modifying this line, and that's not what we want to do. We don't want to modify anything that's passed in. They never change. We only create new results for people. Okay, so now we want to project the point, which is the circle's position, onto AB, which is the line segment, and then come up with some parameterized position T. Okay, so we're going to say vector 2f circle to center, or circle center. We'll call that circle to center. No, circle center. And that's just going to be the circle's rigid body get center. I forgot we had created that. So circle.getCenter, which will give us the center. And then we can say float t equals new vector 2f. We'll pass in the circle center dot sub line dot get start. This is going to be the center to the line start. We can actually create a new vector out of this too, just so that we're completely explicit. So we'll say this is center to line start, which is just a new vector. And then what we want to do is we want to dot this vector with AB, and then we want to divide by AB dot AB, right? So then we'll say float t equals, and then we're going to say center to line start dot dot, and we're going to dot it with AB over AB dot dot AB. And the dot functions do not modify the vectors. You can click into it and see that it's not modifying anything, so you don't have to worry about messing anything up with that. Go back into here now. Okay, so now we have our t variable. We're actually going to check and see if it's on the line segment. So I know in the previous video I said that we're not worrying about whether it's on the segment or not. We might change that, and we actually have to change something else in here too, because we do have a bug waiting to happen. So we're going to eventually change everything so that we are working with line segments, not lines. So first what we're going to do is check if t is less than 0.0 or if t is greater than 1.0. Remember, this is a percentage of the line. The t is the percentage line. So if it's less than 0, greater than 1, what that tells us is it's not on the line segment, right? It's somewhere off of the line segment. So we can just return false out of here. But if it's between that, then we know we're on the line segment. So then we're going to say find the closest point to the line segment. And what we're going to do is we're going to say vector 2f line segment equals a new vector 2f line.getStart dot add. So we do line start plus, and then we want to do AB times our t value. Exactly what we talked about. It looks a little bit bigger because of everything we have to do, but yeah. Okay, and so this is our closest point. And then we can literally just return point in circle, closest point. I don't know why I called this line segment. This is the closest point. So we'll give it the closest point, and we will do our circle. Okay, and that should do it. So this will check whether a line and a circle are intersecting. Instead of going into the line versus box 2D, I did that, and it's actually worthy of its own video because of how long it takes. I'm going to talk about unit tests. So one of the ways that we can test that these things that we've been coding, these functions, are working is by creating a test suite and doing some unit tests. This will make sure that we catch all the edge cases, as we'll see in this test right here. And it also just makes sure that if we ever change these in the future, that these tests will run and we'll see that we may have broken them or something. So, and the way you set up unit tests is actually pretty easy in Java. Okay, so let's go first into our test package, which should come with IntelliJ by default. If you're in a different IDE, I'm not sure exactly how this is going to work. You're going to have to look it up with that specific IDE. But let's continue with this one. Okay, so I'm just going to go into test Java and create a new package and call this physics 2D. And then inside of physics 2D, I'm going to go ahead and create a new class, and we're going to call this collision detector tests. So this is going to be the test suite for our collision detector. Now, in order to test these classes, we do need to modify our settings.gradle file, or not settings, but build.gradle. Because we are going to be using JUnit to do our testing. And so in order to get JUnit to work, we simply need to add it into our dependencies inside of our Gradle file. So we'll just say JUnit so that we know that this is for JUnit. And then we're going to say test implementation because this is our test suite. So it's not for implementation, but for test implementation. And I'm just going to say JUnit and JUnit 4.13. So this is the exact version I'll be using. Then I'm going to hit import changes. Let that run, and we should get a build successful. Let's just make sure that worked. All right, so we got configure successful, which means that we should now have JUnit attached to our project. Okay, so now to get this to work, let's go into into our test class that we just created, and we're gonna check and see that this is actually working. So first of all, we're gonna go in here and we're gonna annotate that this is a test using @test, and I'm just gonna say public void test. This is gonna be our first test. We're gonna say assert true, and then I'm just going to say true. So this should pass. There should be nothing that should break that. And then you're going to notice that we can import this from JUnit framework, which is where we're going to import that from. So this should work fine. Now that we have the test here, let's just run this to make sure it works. So you'll right click over here under physics 2D, and we'll right click on the class itself. And then we'll just hit run collision detector test. So if you run this, what you should see is that it should say tests passed down here. Now, if I minimize this, if you go up to the top bar and hit run, and then you hit edit configurations, you'll notice you have this new thing popped up. You should have application, your main application, then you should have Gradle and something that says collision detector test. Click onto your main application, and now we'll add one more step to our build. So right now what's happening when you hit Shift F10 is it runs this. It builds your project, which means it compiles it and then it runs it. Then we're going to go down here and we're just going to hit the plus button, and we're going to hit run another configuration, and we'll hit collision detector test. All right, so now what's going to happen is it's going to build, and then it's going to run our collision detector test. And then if they pass, it will run our program. So now that that's done, I'm just going to hit apply and then hit OK. So if we run this by hitting Shift F10, what you'll notice is it shows a little green bar for a very split second that says test passed. Now, if I were to set this to false, this test should fail. So if you hit Shift F10 now, you'll see it says test failed, and it gives you the description. So now that we have a way to write tests, let's write our first test. And this is very simply just going to test our first function. So I'm going to write it, and the way you should name your test is the test name. So point on line. So this is what's happening. Should return true. Test. So what I'm saying here is there's a point on a line, and I could say line 2D should return true. And so I'm just going to mock up my variables. So I'm going to say line 2D line, and we're going to import this, equals a new line 2D, and I'm going to give a new vector 2f 0, a new vector 2f, and then I'm going to say 12 4. Next, I'm going to create a point. So I'm going to say vector 2f point equals a new vector 2f 0. This point is definitely on this line because we have the point 0 as one of its points. So then we're going to say assert true, our intersection detector 2D dot line or point on line. And then we're going to give it our point, we're going to give it our line. This should be true. And then if I hit Shift F10, then this should still pass. It passes, and we know that's true. Now, how do you pick your test cases? So what I did here was I know this is going to work, but is it a good test case? Some would argue no. I would say yes, because we're testing that if it's an endpoint, it should return true. That is testing one of the parts of our equation that should work. So in terms of line 2D, some tests that I think would be good are testing the endpoints. Those are easy. You know they should return true. So we could copy this, paste it, and I can call this test 2. And then we'll just say 12 4 should also be on the line. You can run this again. It should return true still. That's a good test too. Then you would create another test. I would say another good test would be a vertical line. So this was actually pointed out by Nikhil. I'm sorry if I said your name wrong, but he pointed out a bug in our code. So this is a great test. We should test if a vertical line still works. So if our line goes from 0 to 10 0, or that's actually horizontal. Okay, so if it goes from 0 to 0 10, goes straight up and down by 10, then 0 5 should definitely be on the line. Let's see what happens. If we run this, we get test failed. Why did the test fail? And then we'll look in here. It says assertion failed error, and then it says collision detector should return true. So let's actually click into the function. I know exactly why it's failing at this point, but you may not when it fails like this. And so if it does fail like this, what I would suggest you should do is go ahead and move this out to its own line. So we would say copy this, and then we'll say Boolean results equals, paste it, and then we'll just say assert true result. This way we should get a little bit more of a helpful error message. Okay, let's check this again. And it's simply just telling us that it didn't return true. So if we go into here, the reason it's not working is because we're actually getting a infinite slope. So if we print out m and see what happens. Okay, there we go. So I thought we would get a divide by 0 error, but I guess Java doesn't do that anymore. So what's happening here is m is actually infinity. So our slope is infinity because we're dividing by 0 here. Now, this is going to be kind of hard to figure out, but this is why the test cases are good, because you would notice, hey, there's something wrong in this specific function, and then you would start printing stuff out inside here to see what's wrong. So if m is infinity, that's because dx is 0. So what we should do here is say dx equals this, and then we'll say if dx equals 0, or we can use our compare function. If jmath.compare dx, well, okay, we shouldn't use our compare function here, because if it's not 0, then we want to keep it whatever it is, okay? So if dx is 0, then we just simply want to make sure that we set m equal to, we want to set dx to something really small. So we'll do this. We could actually just do float.minValue, which would be the smallest possible value we could have, and this should get us something close. And now if we run this, let's see if this works. We get a failure again, and that's because we're just going to have problems. So what I would suggest a better solution for this would be is actually, we know the line is vertical, right? So all we have to check is see, it doesn't matter what the y is, it just matters if the x is the same as this line's x. So we can just return point.x equals, we'll do a comparison here. We'll say return jmath.compare point.x to the lines starts x. And you could use the lines end x too, that would work just fine. But this should do the trick too. So now if we run this, we get a test success. Okay, so this is sort of like a very quick primer on just how tests work. I'm not going to write the tests or go through writing tests with you guys because I've already written a test suite. I may release the test suite on GitHub. Mine is actually written for 3D, but I might translate it so that works with 2D stuff, just so that you guys can run the test suite on your code, make sure your code is working so that when we actually go to do the physics, you'll know for a fact your code is working, because if they've passed my test, then your code should work the same way that mine is working. And if you guys want, you could also, if you find, like, make your own test and see parts of my code that aren't working correct, that's helpful too, because then you can let me know that I've missed some edge case that I didn't know about. But in general, more descriptive names, I would suggest this would probably be a better name, like point on vertical line should return true, because you just want to know exactly what you're testing here and just put it in the name. Test functions are the only function I'm going to say should have long descriptive names, and then just work it out by hand and make sure that the results you get match what you believe you will get. One last note, you may want to come up with a custom epsilon. So I'm going to say private final float epsilon equals, and then 0. I believe I have 1, 2, 3, 4, 5 zeros. So 1, 2, 3, 4, 5, 1F. This epsilon will be good for some tests if you ever end up using a square root or something in your calculations, because sometimes you may have the correct numbers, but they'll be off by a very small fraction, and so you'll actually get the wrong result. So just make sure that if you ever have to, if you're using comparison with floating point numbers, you may want to use a smaller epsilon. Okay? But that's been it for this tutorial. In the next tutorial, what I'm going to do is I'm going to go over how to test if a line is intersecting with a box 2D. You guys have some homework, write tests for your code. Make sure that this is all working as it should. And this will also test to make sure that these functions just work, right? So it serves sort of two purposes. I hope you guys liked this. If you did, please hit like and subscribe, and I'll see you in the next tutorial, guys. Okay?